In this lecture now, let me simplify the idea of field a bit. Okay, so you all know about electromagnetic waves. Okay, what do you mean by electromagnetic waves? Light is an electromagnetic wave. But you also know this electromagnetic wave also has a particle nature. And when you consider the particle nature of this electromagnetic wave, so we have discussed this in great detail in our quantum mechanics lecture series. Please go through that. So the particle nature of electromagnetic wave tells you that electromagnetic wave is nothing but a collection of large number of photons. It means if you have a collection of large number of photons, okay, then this particular collection starts behaving like some kind of wave, and when it starts behaving as some kind of wave, then at each point you can represent this collection as a field variable, which is electromagnetic field E of x and t, or in 3D it will become E of x, y, z and t. So a collection of photons, we know that it behaves like a field. So instead of studying the photons individually, we study the overall effect that this collection of photon create. What overall effect this collection of photon create? The overall effect is they behave like a wave. So when they behave like a wave, at each point we can represent the wave with a field variable E, which fluctuates with space and time, and this E must satisfy Maxwell equations. Okay, we have discussed in great details about it. Similarly, if you look at a fluid is a collection of large number of molecules that flow. Okay, so instead of studying these molecules individually, what we did is we thought of studying them, study their overall effect. So the overall effect of this collection of molecules is that they behave like a fluid. Okay, so when they behave like a fluid, each point is now recognized as a point where we have density. So density becomes a field operator or field variable, while density is now a function of x, y, z and t. Not only at this particular point I can define density, but also at this particular same point I can define a velocity, and this velocity, which is a field velocity, is also a function of x, y, z and t. In most of the situation, this particular t is not required because everything changes in space and nothing changes with time. So the variables are only field variables with respect to space. Similarly, this particular point in the fluid, if I talk about this particular point, then this particular point can be defined by two field variables. One is at this particular point I can define a overall density, but since this density may be different than the density calculated at xyz, so I put a dash. And also at this particular point of the fluid I can define a velocity. That means a velocity at this particular point. So what do you mean by velocity at this particular point? Velocity at this particular point means if you keep say if you place a ball here, okay, and at this particular point you calculate what is the velocity of the ball when it was moving through. So you had a ball here and it was moving through the fluid, and you calculate the velocity of the ball at each point. You found that velocity at this particular location, let me call this location as P, is equal to v dash x dash y dash z dash. Now the velocity of the ball at this location may be different, so let me call this as v double dash. Okay, similarly you can see that at each point of the fluid or I can define each point of the fluid by using two field variables. One is density, another is velocity. And the overall motion of the fluid can be described in terms of these two field variables, which is the density and the velocity. One such idea, or you can say one such equation, which is the continuity equation. If you look at continuity equation, it contains terms in density and in velocity. There is no other term here instead of density and velocity. So do you understand? We have this continuity equation that the fluid satisfies, and this continuity equation is made by using these two field variables, which is the velocity and the density. So let me give an extra information. Albert Einstein said that fluid dynamics or the continuum mechanics is the subject that gave birth to field theory. So when you study higher physics, you will study about something called as quantum field theory. So in quantum field theory, what you do is you study with fields, just as this. This is also a part of quantum field theory, where a collection of photons is studied in terms of field variable E. Similarly, if you have a collection of electrons, say you have collection of many electrons, then these electrons are represented by a field variable psi, which is a function of x, y, z and t. This psi, which is a field variable or the field that describes this electron collection, satisfies Dirac equation. Okay, interesting, right? So in electromagnetic field, the field variable, they satisfy Maxwell equation. For the collection of electron field, the Dirac operator, in quantum mechanics we call this as operator. This psi satisfies Dirac equation. And if you go to fluid dynamics, you have rho and v, which is the field variable. They satisfy continuity equation. And there is one more equation, which is the Euler's equation. They also satisfy the Euler's equation, which we'll look in the next lecture. So I hope the idea of field is clear to you.